All right, so today we're going to look at Newton's second law of motion. Before we do that, though, let's go over kind of a misconception a lot of people have with mass and weight. They're often used interchangeably, but there is a difference between them. We're just going to say mass is essentially how much matter or stuff something has. So in other words, if you were to add up all the protons, electrons, and neutrons in an object, that would be what we would refer to as the mass. The units that we use are going to be the kilograms. This is different than you might have used in chemistry where you typically stuck with the grams. We are going to use a kilogram though, which would be 1,000 grams. Weight, on the other hand, this is actually how hard gravity is pulling on an object. So it's a force, how strongly gravity is going to be pulling down on the object. The units we use for force, of course, is going to be newtons. So if you notice in our equation F equals ma, there's our force F and there's our m mass, right? So they are related to each other, they are proportional. But the acceleration that we're going to use is going to be the acceleration of gravity. So we can just say the equation for weight then is mass times gravity. So for example, let's say you're going to lift a 50 kilogram object. That would be the mass of that object. If we wanted to calculate the weight, we're simply going to multiply by little g, which is 9.8. And that's going to give us a weight of 490 newtons. So we'd say the mass is 50 kilograms and the weight is 490. Well, what would happen if we go to the moon? The moon, gravity is less, about 6 times less, so 1.6. So on the moon, if you take your weight to the moon, notice it's still going to be 50 kilograms. That doesn't change. However, if you now multiply by the acceleration of gravity on the moon, you're going to get a weight of only 80 newtons. So in other words, the weight would be 6 times less, even though the mass, clearly how many protons, electrons, neutrons in that weight you're lifting up is going to be the same. However, gravity is going to be weaker, and therefore, in this example, you could lift essentially 6 times the mass you could lift on Earth. So if you could lift, let's say, 100 pounds on Earth, you should be able to lift 600 pounds on the moon. All right, so let's get into the core of the material today. We're going to be looking at Newton's second law. If you remember, this is just F net equals ma, and we're just going to simply define the net force as the vector sum of all the forces. Now the equation we use for this, then, when we add up all the forces, we're just going to use this little summation sign right here. This just means sum up and add up all the forces. Now when we do some more challenging problems later, we are going to make sure that we keep our x and y directions isolated, as we did in the last unit, but we'll go over more of that later. Let's look at a simple example. Let's say we have one person pushing to the right and another person also pushing to the right. We want to know what's the acceleration of this box here. So we'll just simply use our F net equals ma. We're going to sum up our forces. We have 400 plus 300, both to the right. That gives us 700 is our net force. And then we just set that equal to ma. So m was 70 equals a. So 700 equals 70 times a, giving us an acceleration of 10 meters per second squared. And that is going to be to the right. Let's look at a slightly more challenging example. What I'd like you to do now is to push pause on the video, read the question, and see if you can solve this on your own. So push pause now. We have our sprinter. Sprinter is going to exert a forward force of 160 newtons. Okay, it's going to encounter some air resistance, and we know that they're starting from rest. So actually, I didn't ask you to do this, but why don't we do this? One of the first steps really that you should do on most of these problems is to draw a free body diagram. Call it FBD for short. We did some of them yesterday. So for example, we know in this problem that there's a
thrust force, we'll call it F thrust. And actually, we know the number, right? What's the thrust force? 160 newtons, pushing him forward. We know there's a backwards force of air resistance trying to slow him down. We'll call that F air. And that is 50. Now, in terms of the context of the problem, this is really all that's important. But technically, there's actually two other forces acting on our sprinter. What else is acting on the sprinter? Gravity is pulling him down. We can call this Fg, but actually I just gave you a new name for F gravity. What is it? Weight. So you could label this either as F gravity or weight. That's what weight is. How much gravity is pulling down on you. That's what we call weight. There's one more force. The ground. Yeah, the ground is pushing back up. F ground. The ground is pushing back up on us. And actually I gave you another name yesterday. What did I say that name was? The normal force. And actually, why don't we just define the normal force now? This is a force due to a surface pushing back on an object. It's really kind of a reaction force, like in Newton's third law. Like there has to be another force before the surface can push back on something. And in this case, it would be gravity's pushing down and the ground's going to push back up. And the word normal is, it's always perpendicular to the surface. The normal force will always be perpendicular to the surface. Okay, so that's just a sidebar. We're going to get more into the normal force tomorrow, but just, you know, for a little preview. Okay, let's find the weight. So this should be the easiest question on the test. Whenever I ask you for the weight, everyone should be able to get this one right. It should see 100% correct answers. How do we find the weight? Well, it's not quite that easy. I didn't actually give you the weight, but it's still an easy calculation. How do we find the weight? Okay, mass times gravity. Right, so to find the weight, you're just going to multiply the mass times the accelerator, whatever planet you happen to be on. And most of the time we're going to be on Earth in these problems that you do. Sometimes they'll say, you know, what's your weight on the moon? Typically are not going to be using negative 9.8 here. We're going to deal with that negative in a different way. So go ahead and just leave it positive. So what's 60 times 9.8? Oh yeah, pull out your calculators if they're not out yet. Oh, this one, you could probably do this one in your head, right? $50. Okay, so that'd be our newtons, 588. By the way, your weights are typically going to be large numbers, okay? They're not going to be like, okay, I weigh 150 pounds. They're not going to be anything like that. These are a whole nother unit. Okay, letter B. What was B? Find the net force. Find the net force. Okay? Well, hopefully this should be somewhat straightforward. Okay? So just like the tug-of-war problem, we have the sprinter going forward with 160 and there's some air resistance pulling him back. Well, what's his net force? 110. Right, so you're just going to kind of subtract that. So 160 newtons minus 50 newtons gives us a net force of how much? 110 newtons. So that's our net force. Yeah. We should. What direction should this be? To the right is good. Or east is good also. Alright, letter C. Acceleration. Okay, how are we going to find the acceleration? So we're going to use Newton's second law. And this is the big equation of the unit, which basically says F net equals, what's it equal? Mass times acceleration. F net equals mass times acceleration. So notice we were given we just found our net force, 110. Notice that we don't use the thrust force. We use the net force. And you have to be careful in the problems. Sometimes they'll give you like the individual forces, the forward force and the air resistance. And sometimes they'll just give you the net force right away. So just make sure you identify. Look for that word net force. If they give it to you all right away, you can find the acceleration right away also. So 110 equals, what was our mass? 60 times A. $83. Letter D. How fast will she be moving after 5 seconds? How are we going to figure this out? Use our kinematics. Good. So we're not going to get away from our kinematics equations. We're still going to utilize them. Notice, what's our V initial? Okay. What's our time? And what is our acceleration? What's the crossover variable between last unit and this unit? What's the common variable? The acceleration, right? So the big variable, the big equation for this unit is F net equals ma. A is the crossover. So sometimes they'll give you acceleration, sometimes you have to find it. You'll use kinematics from time to time. Okay, which one's going to be good for us? The nice easy one. 0 plus 183 times 5. Nine point what?
1.5.
1.5.
So we're going to try one last example. Once again, I'd like you to push pause, try this one on your own, and then when you're ready, come back and watch the solution. So push pause now.
Okay, so let's look at this one. We have our helicopter going upwards, right? At a certain acceleration. So if we do our free body on this, we have the lift or the thrust. I think I called it here lift, but you could call it thrust also. We have the lift going up, and then what's holding it back? Gravity holds it back, right? So those are essentially the two forces, the lift up and then the gravity or the weight coming down. So in this problem, let's find the weight. How do we find the weight? Okay, mg, right? W equals m times g, that's easy. M was 2,000 and little g is 9.8. Okay, almost 20,000 newtons, pulling down on it. All right. Letter B, let's find the net force. So in the previous problem, how did we find the net force? We just kind of added and subtracted all the forces. In this one, you could do that also. We could say, all right, F net equals the lift minus gravity, right? However, what's the problem with this? I didn't tell you the lift, right? We don't know how much the lift is. So we can't actually use this to find this. What do? What we did give you was the acceleration, right? So there's always going to be two equations for the net force. There's kind of this, what net force means, which is summing, adding up forces. And then there's the Newton's second law, where net force equals mass times acceleration. So you kind of always have two choices. Sometimes you use it one way, sometimes you use it the other way. It just depends on the context of the problem. So in this case, since they did give us the acceleration, we're going to go ahead and use this part of F net. So what was our mass? 2,000 times 18. $36,000 newtons. So that's the net force. Just a concept question. Should our lift force be greater or less than the 36,000? Greater. Why does it have to be greater? Subtracting from the weight. Right. This is when you add and subtract all the forces. And since we're subtracting out gravity, we have to have more lift to provide this kind of net. So let's just finish it up. So now we are going to use this part for letter C. So this part's going to essentially be letter C, right? F net equals F lift minus F gravity. So our net force was 36. Our lift force is unknown. Our gravitational force was 19.6. Remember, gravity and weight are the same thing. Force of gravity and weight are the same thing. And hopefully it confirms what we predicted in terms of the size. Should be greater than 36,000. Looks like we're at 55.6. So again, that was our upward force, 55.6. Gravity's pulling down with 19.6, which gives us a net up of 36. So that's kind of the concept of this. Actually, I should draw these arrows longer just to clarify that this is a huge lift force overcoming gravity and providing some force to accelerate us as well.